I would like to welcome Mr. Mainak Mukherjee, our beloved Mainak Da. He's
Thank you.
graduated metallurgical engineer from our institute in the year of 1970. Then he has served several industries in the field of metallurgy. In 1975-76, he did his master's from Sheffield University in UK, and he has dedicated his rest of his life in the field of metallurgy. Currently, he is working as a senior metallurgical consultant in Lloyd's Register and based in Mumbai. And I'll over to Moinakda to give a light to our current students and all the audience here. Thank you.
Thank you. Thank you, Shukamal, very much. Am I audible to you
Yes, absolutely.
and also visible?
Yep.
Good evening. Is Dr. Munojit Ghosh is there, please? Well, with due respect to Dr.
I'm very much here, sir. I'm very much here. Thank you for coming. Welcome.
Because this will be giving a chance to talk to Dr. Munojit Ghosh and being part of our engineering department. I'd love to offer my greetings to you. So, good evening to all. Our coordinators, Dr. Swarup Kumar Ghosh, Professor Tapindu Mundol, and many thanks to our very close alumni brother, Mr. Shukamal Naskar, and also our student representative, Mr. Mudit Agarwal, and my dear all students. Thank you for organizing this 80 years anniversary of the Department of Metallurgy and Materials Engineering. When I studied and I graduated in 1970, it was only a Department of Metallurgy, but now it is added with the Materials Engineering that is giving us a lot of happiness. As an alumnus of this department, a big thank you to all for inviting me for this presentation. Coming to my topic, it is my first day at industry. It's something very interesting because, I was selected and from the campus interview, and I was at Gaskin Williams, which is a very good organization of metallurgical industries, and I was there in steel division. And the very first day when I had gone there, my senior has given me about 12 millimeter dia, some hot rolled coil samples, and telling me it is ZN8, and please check the DICAR and report to me. And I was at a loss because I was not knowing what is called ZN8 and what is called DICAR. So that is a little, I was at a loss, and I felt that a little sorry also about it. But then I was smart enough to find out everything, and I reported all that at the end of the day. But the next day, I had a complete specification for EN8, which is BS 970-1955 EN8. It is a general engineering purpose, but it is no longer existing now, that particular BS 970 EN8. It is updated. And as per BS 970-1983, called 080M40, but it's a very good steel for engineering purpose. Medium carbon steel, 0.35, 0.45 carbon, manganese 0.62, 0.9, silicon 0.15, 0.30, sulfur phosphorus 0.035 max. Excellent steel in a normalized condition, hardened and tempered condition, and is also equivalent to AISI 1040, which is American Iron and Steel Institute American grade. So, basically, what I just wanted to say about that on the next day, I had the full specification of EN8, and then I will tell you that there is a complete specification called ASTM E10772014. Is a standard test methods for estimating the depth of decarbonization of steel specimens. So I was smart enough to find out on the next day, and then the life was ours, as a matter of fact. So coming to my main topic, which is comprises of some salient points in steel metallurgy. And I'd like to touch upon a few points because the time is quite less, but these are very interesting points. What I realized as a field metallurgist or industrial metallurgist is important for you, that when we look for iron-carbon equilibrium diagram, there's something called austenite stabilizer, that is nickel, manganese, cobalt, copper, etc. That is raising the A4 point. You know that AC1, AC3, AC4, etc. So A4 point is up, and is lowering down the A3 point. So the field of austenite is increasing. So that is why it is called austenite stabilizer. And when we talk about a ferrite stabilizer, which is chromium, moly, vanadium, tungsten, aluminum, silicon, etc., that is raising the A3 point and lowering down the A4. That means the field of austenite is restricted and the field of ferrite is enlarged. And that is why it is called ferrite stabilizer. So normal iron carbon diagram, we have got AC1 at 723 and AC3 at 910 degrees centigrade. But when we add alloy, say we have got many grades of alloys, which I'll be discussing with you. On a forging grade, we have got F5, F9, we have got F11, F12, we have got F91, also called P91, same. It is a vanadium treated steel, which is a very, very emerging material now for pressure vessel and also for heat exchanger application. Very interesting in the field of Shukamol, it's in the welding field, because it is a very crack-prone steel. So we have to take lots of care to eliminate, the cracking tendency at the time of welding. So whenever we have such steel, the AC1 goes to 760 degrees centigrade and AC3 goes to almost about 960, 980 degrees centigrade. I don't have any slides because this is such a small time slide projections and the content what I'd like to give will not be sufficient enough. But I hope that you understand AC1, AC3 and AC4, what I told. And my next point is this, we have studied TTT diagram. My focus of this particular lecture to our beloved dear students, because when they come from institute to an industry, what are the basic problem fields? I'll tell you my little experience also, that out of a big industry, like when I go to Larsen or when I go to BHEL, there are about 1900, 2000 people are working, and there may be about 30, 40 combination of electrical, mechanical engineers, but only 1 or 2 metallurgists. And if there is any failure, any identification problem, any materials related problem, they will come to you, they will respect you as a god, a metallurgist, and will say, sir, these are my problem, kindly help us. So what I'm saying that is your role in an industry. So it is better that when you are graduating, especially to fourth year student, I would like to say that simultaneously, you should have a lot of knowledge on specifications, a lot of knowledge on ASM Metals Handbook. Now you are going through the many textbooks and also our professors' lecture notes and all that. But the moment you are in industry, you are no longer with the textbooks or the notes. You have to, they are the backup material, no doubt about it, because that is giving you a very sound theoretical background. But then you have to go for American Society of Metals handbooks and all the specifications for your knowledge, because the industry deals with specifications, industry deals with the handbooks, basically. So you should be, and I would tell you what I have done. There is a book called Making, Shaping and Treating of Steel. And this was like a Bible for me. Even when I was a fifth year student, in our time, it was a 5 year course. Whenever Dr. Seal used to give us some lectures on physical metallurgy, I'm very grateful to him, an excellent professor. But I used to carry on with the making, shaping, treating of steel. That used to give me the knowledge of some specifications and all that, which was subsequently I find it was useful when I went to industry. Now coming to my next point, that is called the CCT diagram, that is continuous cooling transformation diagram. Now effect of alloy in continuous cooling transformation diagram, we'll find that when we add chrome, moly, vanadium, etc., the diagram changes. And that is very important. There is an atlas of continuous cooling transformation diagram. And for each steel, you can find out what is the nature of the diagram, and that will help you to decide or to design a heat treatment cycle, especially the cooling rate, the starting austenizing temperature, the cooling rate, whether you would like to have a, my subsequent lecture will complete that, whether you'd like to have a hardening and tempering structure, or you like to have a normalized tempering structure, then what will be the microstructure will come, or what you expected out of that, because the microstructure is going to give you the desired properties. So effect of CCT diagram is very, very important. TTT is a basic diagram, but I like to emphasize on a CCT diagram, and there is an atlas. Now coming to solid solution, there are two types of solid solution. One is substitutional solid solution, another interstitial solid solution. Now in interstitial solid solution, carbon atoms, they dissolve in iron. And this particular phenomena we are utilizing for carburizing, which is called surface hardening of steel. Many of the gear components, all that, they require the carburizing, etc. So there, or the carbonitriding, the nitriding, etc. Even nitrogen is also interstitially, it is soluble in iron. So we take help of this particular phenomena, and with the carbon we do carburizing, with nitrogen we do nitriding. Even hydrogen also is interstitially going inside the metal, but that is bad. We do not want any hydrogen or a minimum hydrogen in steel, because that is the biggest threat in the world in basically in steel, in form of plate or a forging or a seamless tubing or fittings, etc., and even for the welds. And very, very important. And we are, we are fighting against how to reduce, even for nuclear application. In nuclear application, I deal with a lot of fabrication jobs. In a fabrication, we can fabricate with a long seam, and that is a welding. But in nuclear vessel, the basic point is this: number of joints should be as limited as possible. And why that is so? Because it is very difficult to control hydrogen in welds. So if the number of joints are less, obviously the amount of hydrogen on welds will be less. So that is why we, for a nuclear application, we have a forged shell. A shell is being forged, such a big diameter, it's about 12 meter, but we have got such a forging shop in India. Also, Larsen2 has got a forging shop in Hazira, which can manufacture. And there the ingot is not a solid ingot. Ingot is a hollow ingot. So the ingot is a hollow, and that ingot is going, and the mandrel is going inside, and that is making the shell. And such big shell is then hardened and tempered to the requirement as per ASME section 3, and then making the properties, and then it is used for nuclear application, for nuclear, the reactors and all that. And that is a place where our services are required. We give such services. And then, of course, hydrogen is another important that, as I told you, that hydrogen should be eliminated, but there are places where heat exchanger or a pressure vessel has to be used where there is a hydrogen ingress. And the design, the temperature of the vessel could be about 700, 800 degrees centigrade. So at that temperature, hydrogen goes in by the diffusion kinetics. And when it goes in, the hydrogen goes and it will cause hydrogen embrittlement. So we have to take care. And there is a test called HIC, hydrogen induced cracking test, by which, and there is an acceptance criteria by which we can select a steel. And then by vacuum degassing of the plate material, we can bring down. Today's vacuum degassing, normally in our earlier days, it was 2 parts per million, but today we have got vacuum degasser, which can bring down the hydrogen to an extent of 0.5 ppm. And the grades are also selective in such a way, and we add some moly, etc., to take care of the hydrogen embrittlement, also at the same time the temper embrittlement, because moly helps in temper embrittlement. So this is a point to be remembered. Then next point is some clean steel concept. Now, whenever we talk about such exotic material which are used for a pressure vessel or heat exchanger or big shaft forging and all that, we must have inclusion controls. And there are 4 types of inclusions. We know ABCD, and you see the chart in your physical metallurgical laboratory. It will be there. And the spec is called ASTM E45 and method A. And these are basically sulfide, silicate, alumina, and globular oxides. And today, a lot of metallurgical work is going on. A lot of metallurgists are trying to shape the inclusions to the desired orientation, so that the fatigue properties and all the basically fatigue properties in steel, when you are having a crankshaft or you are having a connecting rod in automobile industries, or when you have a big shaft, a rotor shaft working in a marine vessel or any other machineries for a vessel, there the fatigue properties are coming due to the stress-induced cycle. There these inclusions play a very big role. So if the inclusions are less in steel, normally the inclusion ratings are 2 max thin series. If you see the T45, there is a thick series and a thin series. So 2 max thin is the acceptance criteria. So all the steel manufacturing units, steel plants, they have to manufacture the steel in such a way that after a plate or a forging or a seamless tubing, whatever we are manufacturing, we should see that, it should meet the inclusion content to that. So that is a clean steel concept. Next is the grain size concept. It's very important. Grain size we measure by a classical method called, McFadden test method. And that, of course, our professors are there, they will teach you. And That is also, there is a specification called ASTM E112-2013, that is for grain size, and the grain size chart must be having there in your physical metallurgical lab. And grain size 1 to 5 is called coarse grain, and grain size 5 to 8 is called fine grain. So normally the steels are of high temperature properties and of low temperature properties. When you take the high temperature properties, preferentially we select the coarser grain size, like grain size 1 to 5. But when we go for a fine grains, the low temperature sub-zero properties, and then we go for a fine grains which are between 5 to 8. And there is a test called Jomini hardenability. Now, this is a very important test. I remember when I was working at Bharat Forge, that used to give me the guidance of selecting for a shaft what is the ruling section, maximum diameter by which when I harden and temper it, I'll get the martensite from surface to the core. That indication you will get only by a Jomini hardenability test. And I would suggest to all the faculty members, if you can have an experimental experiment with the Jomini hardenability in the department, a very useful tool for the metallurgist. And then my next point is called in situ metallography or replica. As we know that we can see the microstructures by a sample. Sample can be seen under a microscope, but there are cases and there are very important scope of inspections or the additional requirement of material that each castings or each forgings has to be checked for a microstructure and to be reported along with the test certificate. There we cannot cut the sample, because if I cut the sample, the casting is rejected or the forging is rejected. Or even a big vessel. Shubpur must be facing those things, a very challenging situation that after welding of a 160 thick vessel, and we like to have, a microstructure of the weld, the heat affected zone and the metal after doing the post weld heat treatment. So that all that can be taken by in situ metallography. You take a replica at any positions, at any time, take a replica of that, bring it to your laboratory, bring it under a microscope, and you can predict all that, you can see all that, and you can do reporting. So this is for the salient points, which is for the steel metallurgy part. Now I'll talk about something on casting. I have to go a little hurried here because there are a lot of things to be completed. So this casting has got a static casting and a centrifugal casting. Now, static casting is more popular and it is isotropic properties. What is isotropic properties? That is no difference for the orientation of test piece. You can take test piece from anywhere and you can take it. It will give the similar result. That is called isotropic in nature. And, there is something called screw. There is a channel through which the liquid metal is poured in the casting. And your objective, the casting should go through a runner and all that, and it will full the entire cavity of the casting should be filled up. Then it will come to the riser. And when it comes the metal to the riser, then we know that yes, the casting is complete and it is a sound casting. There should not be any problem and all that. But life is not so easy, my dear students. The thing is this, that earlier days, it is a job of a methods engineer, and I've seen brilliant metallurgists working as a methods engineer. There they have to position the riser, they position the gating systems, the vent systems and all that. Even after that also, they used to get a lot of defects. And but today, and gradually, we have got some software models, and these are 3D models there. So you go to a good foundry, and a good foundry shop, they have got a software 3D model. Or if they do not have, as a metallurgist, when you join industry, you must advise them that you get that software 3D modeling, so that when the design of that particular casting, you log in to that particular 3D modeling, they will show you where the risering should come, where the ingot system should come, how the runners flow. So the life has become a little easier. There is two important terminology. One is called chaplet, one is called chill. Now, chaplet is a thing, it's a metal insert, it's a mild steel, and that is inserted inside the castings to keep the core steady. Otherwise, with a ferrostatic pressure, when you are pouring the liquid metal, the core shifts. If the core shifts, the casting getting rejected. So to keep the core solid and keep in position, we must have a metal insert that is called chaplet. And then the chill, the purpose of a chill, that there is a directional solidification when you do casting. So suppose there is a thin section and there is a heavier section. So thin section always try to pull faster than the heavier section. So there is a combat, there is a fight between the thin section and the thicker section, and a shrinkage type of defect will be there and the casting will be rejected. So you have to put some chills. Chills are nothing but normal nails, mild steel nails. And they are put in the heavier section so that you try to have the solidification rate of the thinner section and the thicker section almost equal. It cannot be equal, but almost equal, so that the shrinkage will be there, but it is less. And there is a standard called ASTM E446, and that is giving, the acceptance criteria of the shrinkage, the slag inclusions, or the sand, etc., etc. These are the defects which are coming on castings. So you can measure that by E446. There is a lot of slides are there, and that is giving the acceptance criteria. And with that, you can see whether the castings are accepted or not. They are very important for you to understand that. Then the next is the hot rolling of plate. I have covered the carbon steel and alloy steel. Basically, the hot rolling of plate is taken from a slab, but the slab is heated on a reheating furnace. First of all, when you go to a steel plant, you should ask for a calibration of that reheating furnace, because it's very, very important that what is your heating temperature, what is your finishing temperature, and to close the heating temperature, you need the measurement certainty. There should not be any measurement uncertainty. So your furnace should be calibrated, and they should show you the valid calibration certificate to see, yes, 1200, if I set the temperature, it is 1200 plus minus 10 degrees, which is given by API 6A and all that, this kind of tolerance. And with that, you should start feeding your slab, and then you should hot roll. And after rolling, the finishing temperature should be around 920, 930 degrees or so. And you should remember that slab to the finished plate, the reduction ratio must be 1:3 minimum. It's very, very important. 1:3 minimum. And then the grain flow. The grain flow of the plate should be longitudinal, because you are doing the longitudinal, and you should know how to do the longitudinal and the transverse direction measurements also, because the reason is this: all plates, carbon steel, alloy steel, even these plates, tensile testing has to be done as transverse to the longitudinal direction. So you should know what is the longitudinal direction, then only you can take a sample for transverse direction. Now, when I had gone to England first for my training, I was given a square plate, so that you do not know that where is the direction, which is the longitudinal direction, which is the transverse direction, nothing is known. So that is the kind of thing, so on a square, but there are ways. On the square plate, you can find out that how the grain flow is in which direction. So that is by a macro etching. You have to do a macro etching on the corner, and you develop the grain flow. You can see whether which side is the longitudinal, and then you take a sample transverse to that, and that will meet with requirement. So these are the salient points which I had faced in problems, and I try to tell you as a student engineer that when you go out to an industry, that will be very helpful to you. Here also, I have told you the tensile test. Impact and bend test, of course, most of the specification requirements are in longitudinal direction, but there are some supplementary conditions are there where they want impact also in the transverse direction. So the knowing the directions of the grain flow is very important. Similar thing is also on the forging. Forgings are of two types: closed die forging or press forging, and they are also, when you hit the ingot or the billet, calibration of the furnace is important. Reduction ratio should be 1:3 minimum. The grain flow orientation is very important, because when you make a flange or when you make a crankshaft, you are orienting the grain flow on the study of a fiber strengthening mechanism. And here the sample taking is very, very important. And the sample should be very close to a longitudinal sample, although it is not longitudinal, but closer to longitudinal. Like if you do a flange, I understand you have seen a flange, and there is a requirement of flange that you have to take in from the disc portion of the flange, the sample. And if you do the grain flow study there, you'll find that grain flow is little deviated and all that. But then try to see that it should be as close to a longitudinal sample, and there you should start taking the sample for your tensile impact, etc. Next is your seamless tubing. Seamless tubing also, there are two processes. One is the hot extrusion process, another is called hot piercing process. And There also the seamless tube is manufactured by a piercing point, and a solid makes a hollow that is called a mother hollow. Then a mandrel goes in, and with the mandrel you take a finished tube, and that finished tube is called hot finished seamless. So it is also in the longitudinal direction. So the bend flow is longitudinal. The sample taking will be all longitudinal, whether it is an impact sample or a bend sample or a tensile test sample, all in longitudinal direction. There may be a specific additional requirement, but that is an optional requirement. The next is fittings. Now, fittings are of two types. One is the forge fittings, one is the pipe fittings. Now, pipe fittings are normally elbow, T, cross, reducers, returns, stub ends, caps. So I'm trying to familiarize with some of the forge fittings because these fittings are all used in the pressure vessels and heat exchanger and in the piping. They're all in the piping components. When you go for a piping industries, you will see that a lot of piping modules and all that, they will have this kind of pipe fittings. Time is very less. Now, heat treatment of steel. Now, normally, the heat treatment of steel, these are normalizing, annealing, subcritical annealing, quenching, tempering, stress relieving, PWHT, that is called post-well heat treatment. I have added another thing which is called normalizing and tempering. This is not there at the time of the teaching and all that because I carry out a foundation course for teaching for all Lloyd surveyors. But this is very important because alloy steels, mostly all the low alloy steels, are normalized and tempered. And the specification asks for that you can do it by quenching, tempering also, but normalizing and tempering is the most the proper process. Even the welder also has to be qualified on that basis, and that is why there is certain amount of restrictions which we'll discuss in the question answer session. And so normalizing and tempering is important. Stress relieving and post-well heat treatment, the heat treatment cycles are almost same, but the stress relieving is for machining. Suppose you are doing a machining and there are some machining stresses come. You are doing a cold working for a cold drawing operation from hot seamless to a cold drawn seamless. There you have to do the stress relieving operations, and that is called the stress relieving. But post-well heat treatment is mandatory that after welding you should do the post-well heat treatment. So there is a heating rate, there is a soaking time and a soaking temperature, and there is a cooling rate. They are all defined, and that is very important. And I have given main thrust on carbon steel, alloy steel, but there is also another heat treatment called solution annealing, which is meant for austenitic stainless steel. And also there is a stabilizing heat treatment that is also there for austenitic stainless steel. Then comes the mechanical testing of steel. And in mechanical testing, I will tell you once again, the first thing is this, whether your tensile testing machine has a calibration. It is very, very important. I go to so many institutes, even including, not like them, but very big institutes in Mumbai and all that. But first day I had gone for some witnessing at tensile test because that was the requirement. I've seen that the machines are not calibrated. And so many research is going on in that machine. So many tensile results are going on in that machine. So then I have requested that, why don't you do this calibration? Then he said, calibration, yes. Then I provided all the address and everything, and they have done the calibration. So this is very important as a metallurgist. When you go to some tensile testing, first of all, you should see that whether the machine is calibrated. Otherwise, you are taking you to an uncertainty zone yourself. And ASTM E4 is the standard for calibration. There is an IIEST standard also, 1828 for calibration standard. Then the ASTM 370 is the most important standard for carrying out the testing part. What are the testings? A tensile test, impact test, hardness test, etc., etc. Even for a fracture toughness test also, there is a recommendation by ASTM 370. So they are very important. Now, in tensile test, I like to recommend one thing that is called, conventional stress strain diagram. Sometimes you may not get the sharp point. So there you have to plot the 0.2% proof stress or 0.5% load under elongation. So how to do that? I do not have time, otherwise I would have discussed, but this is very important. You kindly read ASTM 370. They will tell you, because this will be very challenging for you when you go to industry, and you will not get for a high strength steel, all quench and tempered high strength, where the The tensile strength is almost about 800 Newton millimeter square, and tensile to yield ratio will be almost about 80%. There you will not get the yield point, and there you have to plot 0.2% full stress or 0.5% full stress. So how to plot that? That is an education that you please read ASTM 370. That they will show you how to do that. Then comes the impact testing. Impact testing also very, very important. That ASTM impact testing calibration once again, and impact testing calibration is to be done by ASTM E23 or ISO 148. And there is a direct verification, there is an indirect verification, but it is important that you should carry out the calibration. V-notch geometry is very important. So this V-notch geometry has to be seen by a profile projector. If there is a notch is not accurate, then a good material will be rejected. It is so important. When I used to go to lab, I have seen the NPCL, the metallurgists and all that from nuclear. They check the dimension. They take about 5 to 6 hours for checking dimension of impact sample, including the notch. But it is required. It is so important because in a nuclear vessel, when you put that particular material, it's a no failure situation. So you have to be very, very accurate in doing all the tests like a tensile test, impact test, fracture toughness test, CTOD test, etc., there. So it is very important. Then comes the hardness test. My half an hour is over. Dear, I will take at least, initially it was 40 minutes. So we are in time. Kindly give me some little time. So hardness is basically the Rockwell, the Fresnel, and the Picus hardness. And there is an ASTM E10 for, once again, calibration of the hardness testing machine. There also it is very important. Suppose you are going to do 200 PHN hardness test, Fresnel hardness. You should take a block nearer to 200 PHN. You should not take a block of 400 PHN and calibrate your hardness testing machine, then go for 200. This mistake is done by many qualified engineers, but that is a little problem. So you as a good man should go to industry, ask for a calibration block, and you should know that what is the expected hardness of that material, and you take a block or that and then calibrate that. Now I'll come to that introduction of welding of steel. It is very important. Now, my humble request to the faculty members that, some exposure of welding of introduction I'm just giving, but some more introduction is needed to all the faculty members, because many of our students, after they're graduating, they will go to fabrication shop. For example, Larsen to PHL and many other good shops, Godrej and Boys and all that. Many welding shops, they will go. So the solid requirement of welding is important. So some orientation in welding is important. So welding meaning the joining together the metal parts by heating the surface to the point of melting with an electric arc and uniting them. Welding commences when an electric arc is struck between the tip of the electrode and the wire. The intense heat of the core melts the tip of the electrode and the surface of the wire close to the arc. Tiny globules of molten metal rapidly form on the tip of the electrode, then transfer through the arc string into the molten whirlpool. Since the arc is one of the hottest of the commercial source of the heat, the temperature of the arc center goes up to about 3,500 degrees centigrade to 4,000 degrees centigrade. And so that is melting the base metal and almost instantaneously upon the arc initiation. If welds are made of horizontal position, which is called a flat, the metal transfer is induced by the force of the gravity, the gas expansion, the electric or electromagnetic forces, and the surface tension. For welds in other positions, like when it is a vertical position or it is on the upper positions, it is a big challenging thing. There, of course, we have to take, it is going against the gravity, and we have to take possible care. The most basic form of welding, and it's a great start for the beginners as student engineers, are called arc welding. And the common process of arc welding are SMAW, called shielded metal arc welding, also called MMAW, that is manual metal arc welding, that is called stick welding, the rod welding. GTAW, popularly it's called TIG welding, GMAW, popularly called MIG welding, FCAW, flux cored arc welding, and SAW, submerged arc welding. These 5 types are important. and we must have this knowledge of this. And the concept is basically there's a preheating, there's the interpass maintenance of temperature, there's a post-heating, and then PWHT. Now, the preheating depends on the material thickness, the carbon content, the alloy content, the resistance to fabrication, hydrogen cracks. It's very, very important. The hydrogen should be as minimum as possible. And the hydrogen level is, in a way, not allowed more than 2 parts per million. Then it reduces the distortion, and then it prevents the shrinkage stress. If my discussion session, if I have time, I'd like to discuss that why ASME code is restricting. Suppose I'll give you the same material. Suppose I'm giving a material of a plate, which is, say, ASTMA 515, grade 70, and I'll give you a 10 millimeter thickness, I'll give you a 25 millimeter thickness, and I'll ask you where the preheat has to be done. And any smart student, he'll be able to tell me that where the preheating is necessary. I'll give you a little fundamental, that when you are striking the arc, and as I told you, the arc temperature is to the extent of 3,500 degrees, the 25 millimeter will work like a heat sink. That means it will immediately take the heat so fast, the cooling rate will be as high as your quenching rate. So metal below the weld will be cooled very, very fast, and the metal will be hard. And this hard will be because of martensitic transformation, and it can crack the weld. So 10 millimeter weld, 10 millimeter thickness material will not require preheating, but the 25 millimeter thickness material will definitely require preheating. So ASME code also limits that for carbon steel, you must have 25 millimeter, any thickness above 25, you have to do preheating. Alloy steel, even less, even 20 millimeter and above, for alloy steel, you have to do preheating. Then the post-heating is very important, because that post-heating is going to eliminate the hydrogen, and post-heating we carry out at 350 to 400 degrees centigrade for about 4 hours cycle, and then followed by PWHT. And when you carry out PWHT, basically the purpose of PWHT is the reduction of residual stress, the tempering of any martensite or penite, because alloy steels will have martensite and penite. So tempering of martensite and penite, and which is adjacent to HZ also. HZ also will have a martensite and penite. So this PWHT is going to temper that martensite and penite, and some removal of diffusible hydrogen. So there are some specification. ASME section 9 for welder qualification, ASME section 2C for electrode specification. Then ASME section 9 also gives WPS, PQR, and WPQT, that is welding procedure specification, procedure qualification record, and welder performance qualification test. And the most important part of welding is called the carbon equivalent. And the carbon equivalent is derived by the formula. This formula is created by International Institute of Welding. That is carbon plus manganese by 6 plus chrome moly vanadium divided by 5 plus copper and nickel divided by 15. And carbon equivalent should not exceed 0.40. If the carbon equivalent is exceeding 0.40, very difficult in weldability, and we'll have cracks in weldability, and welding cracks will come. So we have to be very careful in carbon equivalent. Now I'd like to give a bullet point, and I am close to almost 40 minutes, but here kindly give me this. Corrosion mechanism, just bullet point. Corrosion involves the reaction of a metallic metal with its environment and its natural process. The reaction involved in causing corrosion is electrochemical in nature. Mind you, it is electrochemical in nature. That is anode, cathode, and electrolyte, which you have all studied in electrochemistry. The popular example is a rusting of ordinary steel. To the engineer, corrosion may be regarded as resulting in a variety of changes in geometry of structures or components that invariably lead eventually to a loss of engineering function. For example, general wastage leading to decrease in section. The rust is decreasing, it is eliminating the section. You start with a 20 millimeter thick, it can have to 15 millimeter, and the load is constant, so your stress value is increasing because area is less, so the structure will collapse. So I have dealt with a column which has failed miserably, and the column, you have Now you are hearing a lot of advertisement of TMT. Can some smart student engineer can tell me what is TMT? It is called thermomechanically treated bar. In our time, we never had any. We used to have reinforcement by ordinary bar, mild steel bar, or after that we used to have torsional steel. But now the TMT has come. Kindly read TMT. It is very interesting for you. And that is called thermomechanically treated. And that is going inside the concretizing column. But even then, there is a seepage of water in concrete, and it goes to the TMT bar, and TMT bar will lose its sectional thickness. And if the thickness is less, the normal stress equals to load per area. That means the area will be less. If the area is less, load is constant. So stress value will go up. And when the stress value will go up, that means the column will collapse. So up to that is the corrosion. But it is in the hands of the corrosion prevention specialist. And I have met brilliant specialists, corrosion specialists who are metallurgists. Even I also had to qualify for corrosion studies and corrosion specialty requirement. Then I'll have a little bit of on fracture. Give me a few minutes, 2 minutes, bullet points on fracture. Let me have a sip of water. The fracture is defined as a separation of a solid body into two or more parts under the action of a stress. This process consists of two parts, that is called crack initiation and crack growth. So for the prevention of fracture, it is important to design. It's the designers and the metallurgical engineers, purview to design against the fracture for integrity of a vessel or a structure. If I can given Dr. Ghosh, if I can get a time for working on a fracture mechanics, because that I studied in England, for any industrial metals and alloys, there has to be some defect. You cannot free of defect. But the integrity of the vessel, we have to deal with, we have to live with this defect. But we have a science called fracture mechanics, by which we can determine what is the shape and size of the defects which we can accept. And still we get a life of a vessel, or a marine vessel, or a ship, or even a static vessel like our your pressure vessels and your heat transfer vessels and all that. So they are all guided by the fracture mechanics. So there are two types of fracture. One is called brittle fracture, one is called ductile fracture. Now, brittle fracture always, it is below the applied stress is below the yield strength, and it's very, very fast. The fracture goes 1 kilometer per second. Mind you, the fracture rate is so fast. But ductile fracture is always accompanied with a large amount of plastic deformation, and failure will only occur when the applied stress is more than the yield stress. And this failure mode is slow and little stable. And steels will undergo a ductile to brittle transition temperature, which is very, very important for you to know. That I should not say much time because time is not there, but Titanic, and in the second Titanic, that I work incidentally in a place where I have to do a lot of marine materials and design of marine materials. Now it has been studied in sea, the minimum temperature with the floating icebergs and all can go up to minus 70 degrees centigrade, not beyond that. So we have to design a steel which can go as minus 70. So there is no ductile to brittle failure. So I will stop there only for ductile to brittle. Titanic ship, at that time, nobody knew that there is something called ductile to brittle. So the ship was not designed and the material was not selected to see what is the ductile to brittle transition temperature. And we had a Titanic failure. Similarly, in the Second World War, the aeroplane used to go and they just vanished. And people were not knowing where the plane has gone. Then the study is way back in 1940, 45 and all that. Some concept of build-up of fracture mechanics has come, and then they found out that they are all ductile to brittle transition has taken place, even for the aluminum and aluminum alloy by which the aircrafts are made. They undergo fracture mechanics, and the fractures have taken place unnoticed and vanished, and then we build up the concept of fracture mechanics, and that is all for today. And I thank you very much for your patient hearing, and I thank the organizing committee for giving me this scope of talking to you. Thank you.
Thank you very much, sir, for such an insightful talk. Sir, if you don't mind, we would ask our curious viewers to ask you a few questions. Is it okay, sir?
Absolutely.
Over to Ritam.
Hello, sir. We have a few questions for you. The first question is, how can we relate our theoretical subjects to industry given the current situation of COVID-19?
Well, whether it is a COVID-19 or non-COVID-19, I would say that because we are doing remote-based inspection. Today, I am with a seamless plant in Jubail, which is in Saudi Arabia, and I am doing the vendor assessment by means of doing, by virtual mechanism, by using my WhatsApp mobile. There, they have got a very good video camera. They are showing. I'm interviewing the people to know to study their depth of knowledge and all that. So even a COVID-19 situation also, I am doing certain tests. I am asking for a impact test or for a tensile test. As you know, the tensile test, when you're carrying out it, there's intricately, you get a graph. And in that graph, they can send it by scanning and all that, and you can study the graph, whether what is the tensile strength, what is the 0.2% full stress, or what is yield strength from the graph. And they will show you either it's a good machine, like Instron is a good machine, they can give you a graph from the machine itself. Otherwise, you have got the extensometer. By extensometer, you can plot a graph, and all that can be, and then from that graph, you can do that 1.2% full stress or 0.5% as per the requirement, and that all that you can see by the virtual mechanism. So COVID-19 is not a very big threat from so far the material is there, but it is definitely a threat because the social distancing and all that is difficult. At Bombay, I would say that there is the industries, they open with a small scale people. The people are going, but they are maintaining the social distancing. But I would tell you that there is an excellent scope of the Make in India or a Made in India projects after the COVID-19 when it is there, because there is a feeling of not buying materials from China. So Indian engineers, Indian metallurgists can do a havoc, I can tell you, if they would like to do. I stayed in China for almost 5 years from a Lloyd's role. The difference is there, the 40% the ladies, they are working, and lady metallurgists, lady welding specialists, lady engineers and all that, and in a very, very cheaper rate. That is the success story of China. I do not know in India that may not be feasible, but there is a tremendous scope of development of lot of materials, various different kind of plates and all that. And I would suggest in this case, my dear gentlemen, and my request to the faculty members that you should do some project. There are two emerging materials, which is called HSLA, high strength low alloy steels, or a little micro alloy steels, and called duplex stainless steel. These two are very emerging material, which has got a tremendous amount of popularity and use. So as a graduate engineer for your project and all that, I request the faculty members that you can do some project on HSLA and also on duplex steels. Yeah, your next question, please.
Yes, sir. The next question is, as a very much experienced metallurgist,
Are you happy with the answer? Are
Yes,
you
sir,
happy with the answer with the previous question?
it's
If you have
actually
any
a question from the participants, sir. It's actually a question from the participants.
Okay. So the participants are happy, or if you have any further question, you can ask me, please.
Yes, sir. We have another question like, as a very much experienced metallurgist, what is your opinion about industry-oriented courses and industry collaboration with our department?
Oh, this is very, very, very important. My earnest request to the faculty members that they must organize the industrial lectures. The authorities of industry, they must come. This is very, very important, and followed by industry visits. At our time, I will tell you today that at our time, this in Howrah, this called Religious Road and Shalkia and all that, they had, like a home industries, they had got so many foundries. And we had the privilege of going over there, and we have been taken to Tisco Jamshedpur also. And we have seen a steel plant as when a fourth-year student, we had gone to Tisco Jamshedpur. So many of the ideas were cleared by these industrial visits. So my earnest request to the faculty members that you must organize the industry visits and also the industrial lectures by the good people, knowledgeable people. Yeah.
friendly conditions are being enforced everywhere.
Can you repeat the question once again, please?
Sir, the question is, what is the prospect of freeze casting? Since now environment friendly conditions are enforced everywhere.
Freeze casting, I'm not able to understand. Kindly clarify.
So freeze casting.
What is freeze casting? We have static casting, we have centrifugal casting, and the castings are made of materials. Like you have steel, you have aluminum, you have magnesium and all that. And you have got alloys of magnesium, alloys of copper. All castings can be manufactured. And alloys have freeze casting. I've never heard of it.
Okay.
Yes, sir. Freeze casting is actually a form of casting where it's also known as ice templating. It's actually a highly anisotropic solidification behavior of a solvent. Usually a ceramic is involved, but it's not yet implemented to metals. We were asking whether since this casting process does not involve...
I think powder metallurgy is the answer. Yes. I can tell you dear, I can give you my, but I have done some powder metallurgy study in England.
Yes.
Powder metallurgy is very important because now we have heard of a connecting rod which is used for the automobile. Now, whenever the connecting rods are used by forging, but whenever you do a forging, there is a parting line comes, and this parting line during forging, if there is a shift, the connecting rod will not give you light. So the forge connecting rod has been replaced by the powder metallurgy by incipient fusion and by a powder metallurgy technique where the parting line concept is not there, and that has given a very good light. And one very important point for a powder metallurgy, that is called isostatic compaction. You have to do a compaction of the powders. First of all, the powder, the size of the powder is very important. That should meet your specification requirement. Then you have to compact. There is an isostatic compaction method by which you have to compact. Then you have to go to a temperature which will give you, it will melt, and that is called incipient temperature. This is the incipient temperature, is a term which is correlated with the powder metallurgy, and with that the metal will melt and they will become sound without any porosity or any slag or any difficulties and all that, and you will get a sound powder metallurgy casting out of that. Yes, please.
Thank you, sir. Thank you for your answers.
Thank you.
Thank you very much, sir, for sharing your time with us. Team Reminiscence is very grateful to you for your time and consideration, and most importantly, sharing with us your invaluable experience in the industry as a metallurgist. Thank you very much. Thank you very much, sir, for your guidance.
It was all focused to the students. So I found that whatever, as a student, whatever discrepancy I had when I gone to industry, and I tried to see. Even today, I am the main mentor in Lloyd register. So my students are from UK, Germany, and all over the world. And they come with this kind of questions and all that, but they are very happy with me because any problem is coming, they're calling me from Germany. They say, sir, I had this problem, kindly tell me and rectify it. So I would say that should be the spirit. And metallurgists, as I told you, that only one metallurgist against 1,500 engineers, 1,500 people, and out of about 40-50 engineers. But you will be respected as a god in an industry. So your role is very, very important to know the things, to apply the things, apply your knowledge, apply your theoretical knowledge into practice and give them a solution by which they are benefited. Thank you.
Very well said, sir. Thank you. Thank you very much, sir. Thank you.
Thank you.